So today we're going to talk about higher form global symmetries. But before we do that, I figured it might be helpful to do a quick review of sort of everything we did yesterday. Yesterday. All right, cool. So, so yesterday we did ordinary symmetries in quantum field theory. So we talked about the action of a G symmetry in a d-dimensional theory, where G acts on some set of local operators, which I either call phi or psi, depending on the example. And the way we realize this is, or we finally ended up talking about this, is in Euclidean quantum field theory, where there we only care about the action of the symmetry on the operators. And there we found that there was some topological operator called UG of sigma, which is the what we call the symmetry defect operator, which I'll just write as SDO for the rest of forever. And so the point was that for every group element, you could define one of these operators on any sigma, which is a d-1 dimensional manifold. And the way it acted on local operators was by surrounding it and then sort of pulling it through so that when there's the intersection point, the exponentiation, the integral of j on sigma, that gives you the action of the group on phi due to the ward identity, which is also known as Mandelstam. Very good. So this is what we talked about for most of the day. And at the very end, I introduced a notation called differential forms. So there we sort of can simplify a lot of the equations we did to derive all of this structure. So we're talking about how there is the G symmetry implies some conserved current. And in terms of differential forms, that would say J mu you can write instead as some J lower mu, which I'll write as J sub 1, because it's a 1 form. And then the conservation equation is the same thing as saying the exterior derivative of J1 is 0, of star J1 is 0. So this is sort of how you would rewrite this equation in terms of differential forms. And then UG sigma is literally just written as EVI integral alpha of star J1, because star J1 is a d-1 form. So you integrate it over a d-1 dimensional manifold sigma. And then you could show this as topological by looking at a sigma deformation, which you end up finding is EVI alpha of star J1 of sigma plus delta sigma minus star J1 on sigma. And then you use Stokes theorem, thank you. And you use Stokes theorem to show that this is equal to the EVI alpha integral of d star of J1 on manifold gamma. So picture here is we have some manifold sigma here, and we think about giving a little bump. This is sigma plus delta sigma, and then the manifold that's going in between the two of them is gamma. So now using the conservation equation, we find that this is trivial.
So question?
Yes?
The hot star operator is metric dependent, right?
Yes.
So in what sense is this topological then?
Yeah, so this is actually something I complained about the very first time I taught this. is that actually, it actually makes sense to talk about having a D minus 1 form that's closed, and that's your topological current. Because, so the natural thing to have for a current is a vector, and then it requires the metric to go to lower, but then sort of the Hodge star undoes that. Because the Hodge star has you have to sort of re-raise.
Yeah.
So, yeah. So really, this looks like it's metric dependent, but it's secretly not metric dependent. It's like just bad derivation, I think. But it's what everybody uses. So, yeah. And then importantly, since this is just the exponential, you can show that, and we know it's topological, there's a notion where we can take product of these, and you find that it obeys the group law. Just by literally taking this and adding their exponentials. Okay. Good. So that's everything we did yesterday. And I want to emphasize that the symmetries that we were talking about are explicitly acting on local operators. But more generally, you can have symmetries that act on higher dimensional operators. And these are what we call higher form symmetries. So for a higher form symmetry, you have to specify the dimension of the operator, that your dimension of your operator that your symmetry acts on. So you have some integer p, some non-negative integer p, which is called the degree. And then you also have to have some sort of group that acts on these operators, G. Yeah. And then together, this is often written as G upper P, and this is called a P-form global symmetry. Yeah, so also, now that we're talking about differential forms, I want to point out the horrible notation or convention of the field is that these are called P-form symmetries. And that's a horrible name because it's not going to be related to anything to do with differential forms, kind of. In fact, they're going to be very confusing because everything with a P-form symmetry is going to have a P plus 1 form. Well, yeah, you'll see soon. Anyways, just note that this is not a differential form.
These standard symmetries are word form symmetries?
Right, good. Yeah. So, good. So, for example, the ordinary symmetries are zero form. Because P-form symmetries act on P-dimensional operators. And so a local operator is a zero-dimensional operator. Okay. Cool. So now you want to say, you might want to ask, is that if I have a P-dimensional operator, how does the group act on it? So here we had a symmetry defect operator that enforced the group action by having this sort of call it like linking. And this is this picture is sort of going to hold more generally, although we're going to draw it differently. So right. So maybe it's actually better to have an example before we get started. So right. So we're dealing right now with continuous P-form symmetries. And we'll generally just take this to be U1. And you'll see actually soon that it has to be U1 for a product of U1s. And what's nice, a nice way to sort of to classify or to think about these the P-form symmetries is that there's a conserved P plus 1 form current. So just to ease this into the differential form notation, you would say you have a p-index antisymmetric tensor that's conserved. And you would write this in terms of differential forms, in terms of a p plus 1 differential form where the exterior derivative is hot star 0. Okay. So now we're going to see the power of differential forms. Is that you can just take this formula and say, well, now instead of having a d minus 1 form, I have a d minus p minus 1 form. So you can try to define, again, some symmetry defect operator. Now this is an d minus p minus 1 symmetrical manifold, where again you just write down almost the exact same formula. And again, you can show that it's topologically invariant by literally just following the exact same argument here and just replacing everything with the correct degree. So again, I'm not going to redraw it. We literally just draw the exact same picture and say, well, now instead of being a d minus 1 dimensional manifold, you just imagine it to be a different dimension. So this is again topological. And because it's just the exponentiation of the conserved current, you again see that there is this product. So this is good. And now the only thing we need to talk about is how does this act on the cooperator, or on charge operator. So here we can imagine we have some p-dimensional operator. Let's call it, I don't know, L sub p. Maybe just L. Yeah, so just some operator L. So here I'm going to draw in 3 dimensions. And you can think of this as being like a one form symmetry. So, yeah, so the example you can have in mind when I'm writing a picture is you have a 3D theory with a one form symmetry, and now L is a line operator. So some operator that's wrapped on some one-dimensional curve. And the way you can, so in this theory, the symmetry defect operator is d minus p minus 1 dimensional, which is 3 minus 1 minus 1, which is again 1 dimensional. So what it looks like is you actually have another line. I'm going to draw it like this. So you can put these in configurations that link each other, because you have 3 dimensions, you can take loops and you can link them. And now what you have is a picture that's very similar to this, where you cannot contract, similar to here, where you can't contract the ball all the way to a trivial point without intersecting the charged operator. So similarly here, you can't shrink the loop without crossing L. And so that's exactly the picture we're going to want to have. So imagine just trying to shrink it this way. And then at some point, your symmetry defect operator will literally intersect with your charged operator L. And then after you pull it off, you'll find that this is going to look like the group action acting on L. And again, because this is topological, you can shrink it to a point where it's trivial. And so again, in order to see this, you can use the Ward identity, which is again Noether's theorem. Sorry, I forgot to use those words yesterday. So So classically, you have this conserved current, which we write this way. But now, the way you might say it is that, so the conservation of your current is sort of violated by the existence of some charge operator, which will say it's wrapped on some surface lowercase gamma. And what it does is it transforms the divergence of your current into a contact. So this is going to be like delta, whatever the charge is, Q, delta of x in the curve gamma times LQ of gamma. And the way you can try to derive this is very similar to how you would derive it for the zero form symmetry case, which is you look at the variation of the expectation value of gamma variation with respect to a coordinate dependent background transformation. And if you do this properly, what you find is this. But in order to do this, we actually need to talk about how you would add background gauge fields. So let's not do that now. Cool. So there's one more sort of neat feature about these higher form global symmetries. So imagine we have a p-form symmetry, and we have p greater than 0. So now imagine we want to take the product of two group operators. So say we want to look at G1 times G2 times L. Okay, so here's my L. And now we want to sort of define some notion of ordering. So we can do the sort of radial ordering. So this would be G2, UG2. So it acts first if you contrive to contract it. And then in the same plane, you try to put a second symmetry defect operator, UG1. Okay. So you can first contract G2, and then you can contract G1 and get this picture. I'll write it down. Good. But so now we want to use the fact that these operators are topological. And so what that actually allows you to do is to change the ordering. So you can imagine doing is sort of taking this, like raising it up and then putting it inside just by doing a topological deformation. And since nothing touches, that's totally allowed. So if you do this transformation, then the picture will look like you've changed the ordering and nothing else. So it'll be like UG1, UG2. And so you would say that this is equal to G2 dot G1 L.
You're still in Euclidean space.
Yes, everything from now on will be in Euclidean. Yes, everything will be in Euclidean from now on. So what I've just shown you, though, is that if G1 times G2 is equal to G2 times G1, that implies that G of P is always abelian. And that's just a fact. And there's actually a long and interesting history about this statement. Actually going back to, it goes back to things in string theory. So in string theory, it is believed that there should be some non-abelian version of a gauged P1 form global symmetry. But this shows you that there has to be something that goes wrong, because I literally just proved to you that all one form global symmetries are abelian. But that could be okay, because That's a string theory, and these arguments do not necessarily apply to string theory.
Are you talking about the
2, 0 theory. Yeah. Yeah. So the 2, yeah. I think the 2, 0 theory is a bit strange. So.
In that sense.
Yeah, that's right.
Hmm.
So I have no idea how you would. I mean, that's also one of the reasons why we don't have to write down a Lagrange for it. I think this is like a fundamental obstruction. It might be that it is fundamentally a non-Lagrangian theory.
So you're implicitly saying then that this argument requires a Lagrangian? It doesn't look like it.
No, there's nothing Lagrangian about necessarily Lagrangian about this. It's just yeah. So
that's not necessarily right.
yeah. I can tell you something later that I thought might be a nice way to think about how this works, but I don't think it doesn't work on the nose. Okay. Great. Okay, cool. So I just told you where they higher form P-form global symmetry is. I erased it. But so who cares? It's my refrain, of course. What does this mean? What does this tell us physically? So it's very important that these operators are topological. So the physical content of a P-form global symmetry is that the charged operators are topologically protected. And the way to see that is the following. So imagine, and first actually maybe I should say what I mean by topologically protected. So what I mean is that if you have any sort of charged operator, for it to be topologically protected, it means you're not allowed to cut it in any way. And the reason why having a consistent global symmetry implies that you can't cut it is that you would say, I can link this with some operator that enforces the group, that implements the group action. So you go from here to G.L, all is null. But if you were allowed to cut it, and what you could do is you could take your symmetry defect operator and sort of pull it out through the cut. And then you would say that this is equal, this goes to just the trivial operator, which you could then glue back together. So that would say that this is not allowed to be equal to itself. So, phrasing it differently, if you were allowed to cut your line operator, you would not be able to consistently define a group action. Being able to consistently define a group action implies you're not allowed to cut this because it would lead to the contradiction that you can either act on it or not, depending on if you cut it. That's the statement. Okay. So maybe it'd be nice to do an example. So that you can maybe have something more physical in mind. And so let's do the free periodic scalar. In four dimensions. So here, I mean that you have an action which looks like this, E4x, r squared, d phi squared, over here. And in terms of differential forms, you would write it as r squared over 2 d phi wedged star d phi, which this I'll sometimes just write as d phi squared. Just for notation. Okay, so by periodic, I mean that phi is literally identified with itself plus a 2 pi shift. So since you just have a free field that is only derivatives, there's a zero form global symmetry, which is U1. And it's the symmetry that takes phi goes to phi plus alpha. And if you do the Noether's theorem procedure to compute the associated current, you'd find that the conserved current star J1 is equal to star d phi times r squared. In other words, this is like the momentum density. Okay. So if you write this out in terms of a conserved vector, it's just r squared times partial phi. So if you take the time derivative component, if you're thinking Lorentzian, this would be r squared times phi dot, and that is literally the momentum. Okay, so the local operators that are charged under this, you might say it's phi, but phi is actually, this statement that phi is identified with itself plus 2 pi actually means it's not, you can think of this as like a gauge symmetry, and this is, so it's itself not a well-defined operator. So the operators that are charged under it are actually these operators. So this is invariant under shifts of 2 pi, so this looks like e to the I q phi plus 2 pi I q, and it's invariant if q is an integer. Okay, so these are the local operators that are charged under it. And the symmetry defect operator, as we said, is just, as we, I guess, know now, is just the exponentiation of the integral of the current, which, as I was saying, is just going to look like e to the I alpha times the associated momentum operator. So when you link any of these charged operators with the symmetry defect operator, you're literally just using the momentum operator to enforce a shift of phi. So UG times OQ x is going to be e to the IQ alpha is OQ x. Okay. Good. So this is, I think, hopefully stuff we already knew. But the reason why I picked a periodic scalar is that there's also a higher form symmetry. So there's also a two-form global symmetry. And the associated conserved current here is a three-form whose Hodge stars looks like d phi over 2 pi. Okay, so that's great, and we know this is conserved because this looks like d squared of phi, which as I told you has to be 0 by the anti-symmetrization of the tensor indices. Great, so we have a symmetry. Does it act on anything? And the answer is yes. It acts on cosmic string operators. Okay, so what do I even mean by that? So, okay, so the way you define a cosmic string operator. Okay, I'm using the word cosmic string because that's what I've been thinking about lately. But these are also sometimes called vortices, either Nielsen-Olesen, ANO, string. These are also sometimes called strings. But anyways, the point is that or what?
Topological difference.
Yeah, that's right. These are all these are actually not topological. Well,
Strings.
these ones are topological because
One-dimensional difference.
It's a defect operator, yes. I read as a defect operator. Yeah. So anyways, defects. Anyways, look. Okay. Cool. So the way you think about this is that, so it's a two-form symmetry, so these are two-dimensional. So we'll think about this in terms of some not imaginary. We're going to imagine there is some time direction. And so I'm just going to draw you a spatial slice. So again, we're in 4 dimensions. So the space is going to be like 3 dimensions, which is something I can draw. So the way you define this is you pick a line in space, and you also imagine it extends in totally in time. And what you do is you take a little tube around it. Oops. Say there's some little radius r here. Oh, let's call it some different thing. We'll call it lambda, since r is this parameter here. And you put a tube around the entire line that you drew, and you cut this out of your space-time. Okay? So now that you've cut this out of your space-time, what you do is you take your field phi, and you make it wind around 2 pi as you take a loop here that goes around the circle. So the picture should look kind of like this. So at this point here, you might say that the phi is pointing here, and then here, you might say that phi is pointing. So we're gonna make it go anti-clockwise. So it might be pointing here. So that as you go all the way around the circle, the clock sort of goes all the way through 2 pi. So the boundary condition is that the integral of d phi along any loop that encloses this cutout line is equal to 2 pi times n. So here n is like what's called a winding number. And this is like the charge of the string. Okay.
Sorry, Daniel.
Yes, please.
Should lambda be finite, or could I take lambda to 0 so that it's really just a line?
I mean, it's going to be my UV cutoff.
Yeah, it's going to be my UV cutoff. I was just,
Okay.
Right. So, as Jose was saying, in order to make this an operator in your theory, you have to take this cutoff, lambda, to go to 0, or this scale lambda to go to 0. And what I mean by this is that the energies that you're working at, so, yeah, so lambda goes to 0. And what I mean by that is that the effective energies, and maybe the cutoff scale to your theory, so you can only probe energies that are much lower than E cutoff. Sorry, I'm mixing. I think it's this. Take the limit of lambda, so that, or E cutoff, so that this quantity goes to 0. Yeah. Sorry. So the way you see this is that so E cutoff is equivalent to 1 over whatever the length scale cutoff E cutoff. And then this statement is equivalent to saying that the minimum, so this is like the minimum length scale you can look at. You're taking lambda to be much smaller than whatever the minimum length scale you can look at is. So when you look very far away, it just looks like you have some operator here, even though if you look very, very closely, you'll see that there's a hole missing here based on. So this is how you define a defect operator, and in particular the cosmic string, or a stringlet operator. Okay, good. So now you want to ask, how does the symmetry act? Yeah, how does the symmetry act on these string defects? And the key is the fact that the conserved current is literally part of the definition. So, it's blue now. So now imagine we have our cosmic string here. I'm going to call it S because that's a cool letter, and say it has charge n. So this is what we're defining here. So you have a cosmic string here, S sub n, and say we link it with our symmetry defect operator. And I guess I've been saying that, meaning this implicitly, that here I'm just going to take G as e to the I alpha, which is in U1. So here, what you can imagine is that this is literally going to be e to the I alpha times the integral of d phi over d phi, which is the winding number. So if you evaluate this operator here, this is going to be the phase e to the I alpha n. Okay, so now if you imagine sort of pulling the operator, the symmetry defect operator, through the charge surface, so now you have Sn, and you have your symmetry defect operator here. This is going to be e to the I alpha, again, e to the I alpha d phi or d pi. But now phi does this, this link doesn't actually wind around the symmetry, the string operator. And so this is actually going to be evaluated to 1. And so the point is, there is an action of the group by the fact that this is like a correlation function, and this is another correlation function. They're equal. And we find is that they differ by this phase, e to the I alpha n. So it's kind of backwards from how you might think about it, but the point is that there's an action here with e to the minus I alpha n. And this is how actually most continuous higher form symmetries act, is that really what you have is you have some sort of conserved current, which is just measured by some winding, and you either measure it when it's linking it or you don't when it's not linking it. And that's what all of them do. So, yeah. Does anyone have any questions?
So this is a statement about vets, not about the operators themselves.
Operator, the statement about devs?
The way you've written it, statement about vets, or
Well, I mean, the operators themselves are like a classical field configuration statement. So yeah, I mean, defect operators are yes, symmetries associated defect operators are about devs. But not all paraform symmetries are of this form. We'll get to that in a second. An example of that in a second. Cool.
So here the statement is that the correlation function on the left is e to the minus I alpha n times that on the right.
Yeah, that's right.
And
No, sorry. This correlation function on the left is equal to this correlation function on the right times this.
okay. So why was there a minus sign there then?
In the sense that like this phase goes from this to 1. So I think the arrow is backwards.
Okay.
Yeah. Sorry. Yeah. Good. Thank you. Cool. So again, why or yeah, why? So everything I've just told you about higher form symmetries has been known since I think at least the 70s. Sort of everything here is it's nice, it's pretty mathematical, but the question is, what sort of new power do we have, and why are we talking about this? So Oh, something I didn't review, I guess, was the fact that we now have more math than they did in the 70s. And what this does is it allows us to understand coupling to background gauge fields. And so I hope I had motivated from the other day that turning on background gauge fields is really nice and it gives us information, for example, of ordinary global symmetries. But what we're going to find is that when you have all sorts of new global symmetries, like higher form global symmetries, there's going to be a very rich structure that emerges. So let's sort of plow ahead. So for a zero form global symmetry, that is the ordinary global symmetry, we had a gauge field, looks like the photon, which is just a one form global symmetry. And the gauge redundancy of the photon field, A mu goes to A mu plus partial mu lambda, in terms of differential forms, is A1 goes to A1 plus d lambda. So, and again, lambda is just a function valued in the Lie algebra, and d is just the exterior derivative. Yes, this is also important. The exterior derivative of a function is the same thing as the partial derivative. So that's always very nice thing to keep in mind. So right, so you can couple a theory to a background gauge field by adding a term in the action, which just looks like I over 2 pi is A mu J mu, which in terms of, and d to the dx. But in terms of differential forms, this is just I over 2 pi A wedge star J. And then again, because of this variation, this is invariant under this background gauge variation. So delta, delta S lambda going to be I over 2 pi d lambda wedge star J1. And what you can do is you can sort of try to invert Gauss's law, Stokes theorem, to pull the derivative from here to here. So this is going to be equal to minus I over 2 pi integral lambda d star J1. And then again, by the conservation equation, this is going to be equal to 0, and this coupling is gauge invariant. Great. So we can do the same thing for higher form global symmetries. And it's going to be the exact same formula, except for the fact that the current now is a p plus 1 form. So remember from probably hopefully somewhere on the board that a p form symmetry is a conserved p plus 1 form current. So you can couple this to a background p plus 1 gauge field. So p corresponds to d p plus 1. So again, this is a p plus 1 index anti-symmetric tensor, and it also has gauge transformations. And in differential form notation, it looks exactly the same as the gauge transformation for a zero form symmetry. So here now, lambda p is a p form. This is a p index antisymmetric tensor field, and d is exterior derivative. So this is our gauge symmetry. And this is actually the reason, well, one of the reasons why they call them p-form symmetries, is because the transformation property is a p-form, which you can debate whether or not that's a good idea. Yeah. So good. And so now, again, we can couple it to the theory. by adding a term that looks exactly the same. So you can just write B, P plus 1, H star, J, P plus 1. And just by using the same algebra, you can show that this is a gauge invariant coupling. So this is the way you would consistently couple your theory to a background gauge field. Yeah. Okay, so now we can go back over here to this example, and I can tell you how you would couple this theory to background gauge fields. So here we had a one-form symmetry, or zero-form symmetry, sorry. And so what we can do is we can turn on a current for it. So here, J1 is R squared plus d phi. So what we can add is plus R squared d phi. Oh, sorry, there's a star there. So it'll be A1 H star d phi. And here we have a three-form current, so we can couple it to a three-form gauge field. So then we write plus I over 2 pi B3 wedge d phi. Sorry, I keep writing these 2 pi's, but they shouldn't be there. Or they don't need to be there. I think it's a different normalization. Okay. And also, I actually had slightly lied to you about this earlier equation. There's actually an I here. And that's important because, as we said, this is kind of like the momentum operator here. But the time component is actually I times, it is the momentum operator, but the commutator relation in quantum mechanics also comes with an I. So you actually want this to be, I think it's a minus sign. So you want it, this is actually your displacement operator acting on phi. Anyways, and that gives us a minus sign.
These I's in A wedge star J are because of Euclidean signature, no?
Yes, that's right. Yeah. Yeah, okay. Cool. So now actually what we want to do is to notice that this theory is actually not quite invariant under background gauge transformations. And the reason is that the background gauge transformations of this zero-form symmetry also shift phi. They actually shift phi itself, because you should actually think of this as a Goldstone boson for a spontaneously broken zero-form symmetry. And so the way you can actually fix that is by adding a background counter term, which just looks like R squared A1 wedge star A1 over 2. So in general, in a quantum field theory, you're allowed to add counter terms to your action. So here you're allowed to add, this is what we call a counter term because there's no dynamical fields in it. This is just a function that you're multiplying the entire path integral by. But what it does is it allows us to write, it sort of absorbs all of the gauge invariant, the gauge transformation properties of this term so that it looks very nice. So I'm going to erase this. And you can actually combine these three terms. So the action just looks like R squared over 2 d phi minus A1 wedge star d phi minus A1 plus I over 2 pi B3 wedge d phi. So this, essentially I just added the term to finish completing the square here. And so what we've done is introduced a background gauge field that corresponds to the shift in phi. So d phi and minus A1 is a gauge invariant combination, and that's how you wrote it this way. Cool. And there's one more thing I wanted to point out in this theory, actually. So I'm going to rewrite the action.
Sorry, what, can you remind me, why did we gauge this symmetry?
So we're not actually gauging it. It's we're turning on a background gauge field, which if we had summed over A would look like gauging. So this is not dynamically gauging.
So, okay.
Yeah, so this is, so like if you were to dynamically gauge it, you wouldn't have asked me what to do, you just done this. And so this is how you get there from this general procedure of saying, well, I just add this coupling. So oftentimes you have to add the coupling and then add extra counter terms so that everything looks nice. Good. So now I want to show you one last thing about this theory. So this theory still actually is not invariant under these transformations. So this is like x. So, well, no, it's not. So the background gauge transformations are the ones that send phi goes to phi plus, plus lambda of x, and a1 goes to a1 plus d lambda of x. So this first term is invariant because it's literally the gauge invariant combination. But this term is actually not invariant. And so what we find is that the variation of this action with respect to this background gauge transformation looks like I over 2 pi d3 which d lambda. And so here we added a background term to a counter term to sort of cancel the gauge variation of this term. But it turns out there does not exist any term you can write down that gets rid of this transformation. And this is the statement of a sort of new anomaly. This is a mixed anomaly between a 0 form and a 2 form global symmetry. And these always occur in free theories. Yeah. So if you remember what we talked about yesterday, for if you have a partition function and you say you have a1 and it's dependent on a1 and b2, sorry, b3. If it's not invariant under the background gauge transformations, like here, then we say there's an anomaly. And then the way we said that you can match this anomaly, show that the anomaly is matched between the UV theory and the IR theory, is we can improve it by adding this sort of phi d theory, which is dependent on A1 and D3. And that this total combination, we could call, I don't know, well, I don't know what we want to call it, but this total combination is gauge invariant, and since this 5D term is, the 5D theory is scale invariant, this entire theory is invariant. So this 5D theory is what we often call the anomaly theory. And you can use it to characterize all of the anomalies in your theory. So here, this Z5D, we can write as e to the I over 2 pi B3 wedge dB3 wedge A1. Because it's invariant under the gauge transformations of B3, but it's not invariant under the gauge transformations of A1. And when you look at the transformations here, lambda Z5D, this is e to the I over 2 pi d lambda, which is equivalent to I over e to the I over 2 pi B3 wedge d lambda. So this is the anomalous variation of our partition function from this sort of variation. And so this is often what we call the anomaly. As I said, it's called the anomaly theory. This part is actually called the anomaly. And what it does is it tells you you're allowed to gauge the 0 form symmetry, and you're allowed to gauge the 2 form symmetry, but you can't gauge them both at the same time. Because what you find is that one way or the other, there would be some variation of the action that would not allow you to perform the path integral over the gauge invariant sectors of your theory. Yes?
How did the exterior derivative go out in the variation with respect to lambda of the phi d partition function, the very last step?
From here to here?
Yes.
Yeah, so there's actually two ways you can try to do this. You can try to cancel this, show that the 5D term is invariant by either pulling derivative to this side or upon pulling this derivative to this side. And that's the same thing as saying this is a derivative, but it's the same thing as having a derivative here. It doesn't matter. So what I did here is I pulled the derivative from here to here, and then the 5D term vanishes, but then you get a boundary term, and that's the
The
variation.
boundary there.
Yes, exactly. Cool. Okay, cool. I want to do one more example, and I'm going to go much quicker, because that's what we're going to talk about for most of the next lecture. So, cool. So free quantum field theories are fun. There's a lot of fun things you can do with them. And I'm going to tell you my favorite free quantum field theory. It's not a scalar theory, but it is a bosonic theory. Today we're going to talk about Maxwell theory. Because Maxwell theory is sort of the intro case to studying non-abelian Yang-Mills theory, which is then sort of the intro case to studying QCD. And I think QCD is one of the coolest theories of quantum field theory. Okay, so again, we're going to work in 4 dimensions. And I said we're doing Maxwell theory. And so this is a U1 gauge theory. So in the action, looks like 1 over 2 u squared. And I'm just going to write it as f squared, which I mean f wedge star f, which again, this is a 2 form, and f wedge star f is f tracted with f. Okay, good. So there are 2 equations for this theory. There's the Bianchi identity. Well, okay, so the equation of motion first is d star f over g squared is equal to 0. And then there's the Bianchi equation, which is d of f over 2 pi is equal to 0. So this normalization is fixed by the action. I added this 2 pi for a reason that will be clear in a bit. Great. So I also wrote it in a way that's sort of suggestive. So these both actually look like conservation equations. And indeed, you can think of both of these as some sort of symmetry. Since f is a 2 form, and we're in 4 dimensions, star f is also a 2 form. So these are both some 2 form currents. So this is a conservation equation for, I'm going to call this one E and this one M. This is f over g squared. Sorry, it's always better to work with stars. So star f over g squared, and this is star, this is just f over 2 pi. Okay, so if we think about this in R4, which we want to sort of think about picking out a time direction artificially. And if we integrate star of j e over some asymptotic 2 sphere at infinity, this is going to look like star f or g squared. So I'm just going to tell you what it means when you pull out the indices. This is the integral of the electric flux at infinity. So that's not totally obvious, but it's true. I'll just tell you that it's just true. So if you use this, And this is sort of a bit of an exercise to go through and sort of pull out all the indices, and then you say, you know, so essentially the point is that in S2 at infinity, and this integral pulls out two spatial directions, and star is is essentially the hitting the indices with an epsilon tensor, and so that says that we're actually pulling out the time direction, and that's why this is an electric flux. So similarly, I wrote these very suggestively. If you integrate star of Jm over any two sphere actually, this is going to be the magnetic flux. D will be two sphere. And these normalizations are actually picked out so that these are integer. Okay. And so the reason why I told you that this is electric and magnetic is that these are actually going to be symmetries that act on electric and magnetic probe particles. So for E1 electric, the charged operator is called the Wilson line, which Jose talked about. So the Wilson line of charge Q, which we have to, since it's a one-dimensional operator, we wrap on some curve gamma. This is just defined by integrating the gauge field, A1, over the curve gamma, exponentiating out. This is, we should think of this physically as a heavy charge Q probe particle. And there's actually a nice way to see that. It's a bit long, so I'm not going to do it. And so the way you can think about it is you literally say, you pick a point in space-time and say, I have some particle here, we'll call V. And if you say it has charge Q under this under the bulk gauge field, and then you integrate out the degrees of freedom here, you find that you literally, integrating this out, inserts this exact Wilson line into the path integral. And so that's one way you can derive it. I leave that as a homework exercise to the reader. Cool. So for the E1 magnetic symmetry, right, so we're calling this electric and magnetic symmetry. The charge operator for this theory is the monopole line, which is also sometimes called the Tuft monopole, or in a Tuft line, sorry, or a Tuft defect. The point is that it's a magnetic defect operator, and again, the way you define it is you pick a point, or you pick a line really. But you can think of it as stretching in time, so you pick a spatial point, and then you cut out some small ball around it, again with the size lambda, and you delete everything inside the ball. And then on the boundary, you impose boundary conditions on the gauge field so that there's a magnetic flux coming out of it. And so the way we usually do this is you write down some gauge field, which is just cosine of theta d phi. So this is, and if you, right, so then you compute the field strength. Right, this is another reason why differential forms are really nice. Field strengths are just the exterior derivative of the field strength of the gauge field. You just find that this is sine theta d phi, which is the volume form on the two sphere. So if you integrate around any two sphere that surrounds your defect, EDI alpha integral of f over 2 pi is going to be, so actually we can get out here, I think. then you find that this is going to be just equal to EVI alpha, and then on BS2, the volume form over 4 pi, which is EVI alpha. So here, again, you can sort of, here, and actually also for this theory, or for this symmetry, the symmetry defect operator acts on the line operators by measuring the magnetic or correspondingly the electric charge that's surrounding the charged operator. And when you pull it out, again, you find that there's no enclosed electric or magnetic flux or charge, so there's no flux going through the sphere. And so that is actually how the U1 symmetry acts on these line operators, is by measuring their charge and comparing whether or not there's a flux through them, just like in the case of the string operator. And I'm starting to run a bit late, but I just want to say one more thing, is that as in the other example we did, you can turn on background gauge fields. And what you could do is, we're going to write down since we have a one-form symmetry, we have a two-form background gauge field, so we're going to write V2 of E for the electric, and V2 of M for the magnetic. And they transform under gauge transformations the same way. It's equal to itself plus the derivative of some one-form parameter. And if you follow our prescription for how you couple to background gauge fields, you would find that to the action, we don't space over there, you add two terms. So you add I times, again, I actually lied to you over here. There's another I here. Sorry, an I here. And the reason is that the electric field is the momentum operator for the gauge field. So again, you have to add an I because you're in Lorentzian or Euclidean signature. So, so it's going to be here, there's going to be a minus sign, which star F over G squared. And then here you add I, B, to M, wedge F over 2 pi. So again, you find that this combines with this term. Well, you have to add in another background counter term, but it combines so that the action will actually look exactly the same as before. So I'm going to add here the background counter term, which is going to be V2 electric star V2 electric over G squared over 2G squared. So that the full action is 1 over 2G squared F minus B to E wedge star F minus B to E, and then we have a second term B to magnetic wedge F for 2 pi. So this looks almost exactly the same, except that all of the degrees are different. So you can think of F as like d phi, and you can think of F, you can think of F as d phi, and then all the equations are exactly the same as we had before. And so, just like in the case here from before, the one-form electric symmetry, E to E, shifts it like E to E plus d lambda E, also shifts the gauge field. And that's related to this fact that the electric field is the momentum operator for the gauge field. So A1 goes to A1 plus M1. And another way you can say that the electric symmetry acts, besides measuring the electric charge inside and outside, is that the symmetry actually acts by shifting this Q 1 plus lambda 1. And if this lambda 1 has an integral, which is u1 value, that multiplies this Wilson line by a phase. So this is equal to e to the I lambda times the Wilson line.
I'm sorry, what is lambda 1 again?
Lambda 1 is a background gauge transformation parameter. So,
Okay, yeah, can you write this as a derivative of the scalar function? No, like the
no.
usual gauge transformation?
No, it is not yeah, that's good. That is an excellent question. So this is not a gauge transformation. It is actually shifting in the space of gauge fields. And you want to shift it, right, so I just said this is some transformation property, but you would say that corresponding to u of g, where g is e to the I alpha, when you pull the u of g through the Wilson line, so here's a picture, goes to this. Here you can say the Wilson line goes to the Wilson line times e to the I cubed. And then here I'm saying it's integral of some lambda 1, but what I'm saying here is that this is actually going to be equal to e to the I, e to the I alpha t. This is e to the I alpha of just 2. So you pick, essentially if this is a single operator, it has a lambda that's associated to it that integrates to 1 when you cross.
So basically that thing doesn't vanish at infinity, right? Lambda 1.
Yeah, that's right.
If you go to, spatial infinity.
Yeah, so this is something that we're going to emphasize later, actually, is that u of g actually corresponds to a background gauge field. And moving it does the background gauge field transformation. So for example, here, there's only a local intersection. So you might ask, how does this change the entire phase by some big non-local thing if it only intersects at one point? And actually what's going on is that for this, lambda 1 is actually just equal to it's the step function, where the step is exactly where the intersection happens. So you think of it as just like so if you think about integrating the gauge field along some line, so think of this as like the gauge field. You know, there's some wiggles from the perturbations, but then when the symmetry defect operator actually intersects, what it does is it shifts everything up. Well, it kicks it so that everything gets shifted up. Sorry. No, I said something wrong. It just gives it a local kick, so that there's it looks like a delta function that integrates to 2 pi. And so that's how you get this like local contribution, local intersection that gives you an overall phase that's non-zero. So, yeah, right, so sorry. So back over here, the same computation from before tells you that the action is actually not invariant under electric transformation. And this again tells you that there's a mixed anomaly between electric and magnetic symmetries. And the anomaly you can actually write as I over 2 pi B to electric wedge D B to magnetic. And I think this is actually really easy to stop. And I'm going to tell you sort of for the next hour what this means. So, thank you.
Okay, let's take a 30-minute break. I think that's deserved. I think there's just one issue that